Hello, future data mavens, and welcome to another episode of Fun with Statistics. Well, in this case, it's going to be fun with margins of error. So today I'm going to talk to you, I'm going to show you a more detailed example about how to do the margin of error business and figuring out sample size, because the example number 2 had that at the end, and it was a little more rough than what I would like. Okay, so I have set up this sample size for an election with the margin of error 3%. And in the last example, I showed you a little bit about how to come up with the Z star that goes with this. So remember, the formula for margin of error is your Z star, or your cutoff Z value for your confidence level, times the standard error, P hat, which we know to look like the square root of P times Q over N. Okay, so a couple other things. As you look at this, I talked in the last video about how you would figure out Z star, but I thought I'd draw it a little bit more detailed for this one. So I didn't give a confidence level for this, so I'm going to go ahead and say that my confidence level is actually 90%, because that's a pretty standard one. I'm going to draw my normal curve here. It's beautiful, isn't it? Good job, me. And so the idea is that my confidence level will be the area around my proportional estimate that I'm trying to gauge and capture in my interval. And so if I want 95% of the data nearby it, I actually want this area. I wish there was a fill bucket. To be my 95%, which means the little areas out here together make 5%. And since the distribution is symmetric, just one of them would be half of 5%, which is 2.5%. So then if you wanted to, you could use the inverse normal command on your calculator to come up with the z-score that corresponds with that. So you would want to, or look this up in the table, you'd find the z so that everything less than it would give you 0.025, and the z that does that is actually negative 1.96, and that gives you the negative little twin over here. And then the positive twin would be this one. And we always use the positive one, since we're using standard error and all that is actually a distance and margin of errors as well. Since you'll have both the plus and minus version, you know, it's, if you use the negative one when you do the plus version, it'll come out negative, and that's actually subtraction. And if you did the minus, like you do plus, which gives you the addition. So it actually doesn't matter which one you use. The margin of error doesn't care. It can't tell the difference. So let me scroll down just enough to see this. Okay, so again, I want my margin of error to be 3%. I'm going to use this. And then I'm going to use the worst case scenario proportion of 50%. If you want to know a little bit about why it's 50%, I will do a little bit at the end of this video about why. It's a little bit of a algebra concept that you may or may not have forgotten. So my margin of error, remember, is my z star, square root of p hat, q hat over n. Remember I said I'm going to use the worst case scenario, which is p is 50%, which means my q hat, which is 1 minus 50%, would give me a 0.5 as well. So let's go ahead and fill this out. Remember, I'm searching for n, that's the thing I'm going to solve for. So my m, my margin of error is 3%. 0.03 is going to be my 1.96 times the square root of 0.5 times 0.5, and then all divided by n. So that's my starting. First thing I'm going to do is divide by 1.96. I'm going to cancel these two. And I get that 0.03 divided by 1.96 is equal to the square root. And I'm going to do 0.5 times 0.5, which gives me 8.25 divided by n. And then I'm going to square both sides to get rid of the root. So I get 0.03 divided by 1.96 squared is 0.25 divided by n. And I'm going to multiply both sides by n so that, try to do new moves in different colors. I should have did up here and I didn't. Which gives us these two will display each other because you're both dividing and multiplying by n, so you're essentially doing nothing. Those two are opposite actions and undo each other. So I have n times something, a number, squared is equal to 0.25. So to finish this off, I'll divide by that thing that n is times by, get n alone. This is just how you move things around. And in the end, I get that n is actually equal to 0.25 divided by 0.03 divided by 1.9. 0.9. My 6 got a little messed up there. No, don't erase it all. I don't want to erase it all. Ah. Okay, when you calculate that, you actually get a rather gross number, which I'm going to round up to 10,068. Okay, so that is it. That is how you figure out what sample size you need to get a margin of error of 3%. So the next time somebody says they are doing a poll and they want to know how much error or how large their sample needs to be to get a margin of error of 3%, you now know the answer. Congratulations. So the last thing I'm going to do here, if you are uninterested in algebra behind this on why 5%, then don't worry about this. Okay, so why on earth did I pick 0.5? Well, the answer has to do with finding maxima of quadratic equations. So if none of those words sound familiar to you, definitely maybe you don't listen. I don't know. We do know that p, since it's a proportion, is somewhere between 0 and 1. So that sort of gives you bounds on what it could possibly be. Oh, shoot. Come on. Damn. Now, if you look at this, we're not actually interested in maximizing or finding the worst case scenario for p hat. We're looking at finding the worst case scenario for p hat times q hat, and q hat times p hat actually looks like this, which if you look at it right, so if you multiply this out, that's actually p hat minus p hat squared, okay? And so since I'm looking for the worst case scenario, I'm looking for the maximum. So in order to do that, I'm going to maximize the upper end point, because maximizing off of 0 is just going to give you where it crosses the axis, or aka where it's going to be 0. So I'm going to look at p hat minus p hat squared less than 1. Okay, and now I'm just going to rearrange things so that I can actually do the quadratic formula on this. Or in my case, I'm going to complete the square, because I'm that type of person who, you know, quadratic formula, quadratic schmormula. Okay, so I'm going to add over p hat squared and subtract p hat to both sides so that I get one side is 0, which makes it easier to factor and move things around. So after the smoke clears, you end up with p hat squared minus p hat plus 1. Now what's fun about this is now you get to complete the squares, so half the middle. And then plus, and now what I've really done is if you square this all out, I've added a fourth on accident, so I'm also going to need to subtract a fourth. So p hat minus a half squared, and these are just equal to each other. That's completing the square. Fun times. That was really fast. Oh well, don't worry about it. So essentially all I've done is rewritten that quadratic so that it looks like this. And the maximum of a quadratic occurs at its vertex, aka where it's equal to 0, which would be where this is 0. This vertex is actually 1/2 3/4. So what that tells you is that the p-value that is maximum for p times q, I'm sorry, the p hat value, not p value as in like probability value that we talked about in chapter 10, it maximizes the p hat times q hat, which would be the worst case scenario, is a half. So those of you who like algebra, I hope you enjoyed this video. Those of you who don't like algebra, I'm sorry these last few minutes were a waste of your time. Peace out, homies.